Exponential functions. One way they can exponential growth functions. They can take on the. You guys might have seen them like this, where they have an a naught right here, and you multiply it by e, and you raise it to the kt, and then over here you have like I don't know, a maybe, or a sub n. Okay, and this right here would be the initial population. And this right here would be the current population, like whatever, like however many years, the current population. I'm just going to say pop period. Another way to see it is you can see it with a p, a t, a p of t. So you plug t into this function, and then you have p naught, and then multiply that times e to the kt. Okay, the p naught is the same. It's initial population. It's like it's just the beginning. It's what you start with. Now, Mr. Peterson here likes to put an n right here instead of the p naught because he likes to say naked, kind of like naked, but naked. How do you say it? How do you say it, Francie? Oh yeah, she didn't want to say it. Okay, so naked. One way to remember, this is just one way that might help you remember it. I don't know. So there's two of the variables I haven't described yet, and that is this guy right here, the k, and this guy right here, the t. The t is obvious. That's time. And time could be anything. It could be minutes. It could be hours. It can be weeks. It could be days. It could be months. It doesn't matter. Just as long as you stay consistent with your units. The k is the rate of change. That change can be an increasing rate of change, or it could be a decreasing rate of change. If it's a decreasing rate of change, it's going to be a negative number. If it's decay, so decay, exponential decay would be a negative rate of change, and then a positive rate of change would be exponential growth. So let's read one problem. Actually, we'll do two problems to help us relate this stuff. Now, this is not a calculus topic right now. An exponential function is algebra 2. A lot of these problems you'll be able to use algebra 2 for. Okay, but there's something special about exponential equations, functions, when you take the derivative of them. They're special. There's a special differential equation, so that's why we review them again. It says the theme restaurant in a town, whatever, is being tested by the health department for cleanliness. Health inspectors find the men's restroom floor to be a fertile ground for growing bacteria. That's disgusting. Okay, now this is the key right here. They have determined that the rate of bacterial growth is proportional to the colonies. Okay, right where it says is proportional, the rate of bacterial growth is proportional to the number of colonies. That's huge. Proportional. Do you guys know what proportional means? Like, okay, let me pull out a geometry example to try to help explain. If I have this triangle right here, and this side is 20, and this side is 12, and this side right here is 24, and then I have this other triangle, and this side is 5, this side is 6, and this side is 3. This triangle is proportional to this triangle. Why? Because I can say triangle 1, to get triangle 1, we just have to take triangle 2 and multiply that by 4. So this is the constant of proportionality. In our case, this is the k. And yes, it does relate to this guy. Okay? That is the same as our rate of change. Okay, so whenever you see this, they have determined that the rate of bacterial growth is proportional to the number of colonies. That means that we have a differential equation that can be gotten by an exponential function. So they just said this, the rate of change, what is it? The rate of bacterial growth, the rate of bacterial growth. So let's say dB for bacterial growth over dt, since it's a rate, equals a k times bacteria. So here's bacteria, there's the k, there's the rate of change. You see how it's related to this triangle idea right here when you're scaling a triangle? So they planted 10 colonies and come back in 15 minutes. When they return, the number of colonies has risen to 35. How many colonies will there be 1 full hour after they planted the original 10. Okay, so let's highlight our numbers here so we don't get confused. So we got a 10 right there. We have 15 minutes right here. We have 35 right there. A full hour. That's a number right there. A full hour, and then we have original 10. Okay, so in order to figure this out, what we're going to need to do is we're going to need to get an exponential equation going. So we know the general format is the population of something is naked. Okay, so this is your initial amount. So what was our initial amount? What is that given to us? It's 10, so we have 10, and then it's e to the k. We don't know what k is, but we do have a value of t, because then we have a value of p, our current population, which is 35. It's right over here. It says it's risen to 35. After how long? 15 minutes. So what's our time units? What's our units for time? Minutes. Okay, so don't forget that. So now we have to find k. Now, how did I know to use this? I knew to use that because it says that the rate of bacterial growth is proportional to the number of colonies. That right there is key for saying use an exponential function. Now, we're not even going to use calculus now. Now, in order to find a function of t for the population so that I can figure out how much bacteria growth there is after 1 full hour, I want to plug in 60 minutes right here eventually, and I want to plug it into something over here so I can find out how much population or how much bacterial colonies there are. So I have to find this value of k in order to do that. How do we do that? Oh, well, first we're going to have to get that e alone by dividing both sides by 10. So if I divide both sides by 10, I get 3.5 equals k. Well, that'd be 15k, right? 15k. Kind of sounds like a lot of money or something. Now, if I'm trying to... Oh, wait. Nope, I messed up. I forgot that e. E. 15k. Okay, how do I get rid of the e? What is the inverse of e? Natural log. So I'm going to go natural log of both sides. Natural log, see, I can take this guy and drop him down to the front, so it would be multiplying. And then what would natural log of e be? What power of e gives me e? That's what that means. Here, let me rewrite it. I don't want to go too fast here. So we have 15k times natural log of e. Got to do a little bit of reviewing with natural logs there really quick. Natural log means log base e. So if I have log base e of e, what does that equal? What power of e gives me e? Come on, tell me. What power of e? Yes, it's 1. So this is just 1 right here. So 1 times 15k, that means it just goes away. That's why you can just cancel it out. If you didn't know that, now you know. Okay, then I divide both sides by 15 to find my k. My k has a nasty, nasty number, but we can work with it. We started out with 10 e to the natural log of 3.5 divided by 15. That's your k. Ew, disgusting. But now I have a function of t. Now I plug 60 in, so I'm plugging 60 in right here. Now you just got to throw stuff into your calculator and tell me what your answer is, and that's going to be our answer. All right, guys, let's practice. Let's practice plugging stuff into our calculator. Pull it out. When you guys do this, when you plug into your calculator, you're going to say 10 times, and then you're going to put this stuff in parentheses. Now, whenever I have fractions, I like to put the numerator in parentheses and the denominator in parentheses just because I'm picky like that. Then you're going to have parentheses around the whole thing to make sure that all that stuff is inside the exponent. Okay, so you should have got 1,500. Point, is it 625?
0.625, yeah.
Okay, colonies. This is what P equals at 60 minutes. At 60 minutes, that's our population of colonies.